Hello everyone, very good evening. So in continuation of yesterday's first session on reading the PhD thesis submitted by Himanshu Ranjan Das on design of directional coupling based silicon optical modulator. Today we will study chapter 2. Himanshu, can you mute right now?
Yes, sir.
Yeah, thank you. So today we will begin to read chapter 2. In chapter 2 basically consists of basic block diagram approach of optical communication, followed by various types of electro-optic effect occurring in the optical modulators. Some of the electro-optic effects are Pockels effect, Kerr effect, electro-absorption, and carrier density based electro-optic effect. Then after that, some losses occurring in the optical waveguides like absorption, radiation, and scattering losses will be discussed in brief. After that, the performance matrices of optical modulator like insertion loss, extension ratio, figure of merit, and energy per bit consumed by this data will be discussed. Then different types of modulators depending on the material used with respect to their structures. Then coupling phenomena in directional coupler based optical modulator. Then we will go through the what are the applications of these optical modulators in present scenario of optical communication. So this is the in brief things, and now this is little bit more loaded with technical terms, but on the other hand it is more comprehensive. Whatever terminology you have heard in chapter 1, now we are trying to comprehend with examples, with different phenomena. Now we have widened our scope to accommodate various types of electro-optic phenomena, various types of optical modulators, what are the performance characteristics, design parameters, and then applications. So with this, now I would like to invite Himanshu Ranjan Das to proceed. Over to you, Himanshu.
Okay, a very good evening to all of you. So today we are going to discuss the chapter 2 of our thesis, which is electro-optic modulators. So let us first go through the introduction. In this chapter, various optical modulators and their properties are discussed. Also, different types of modulator technologies and the behavior of different material-based optical modulators are presented. Various optical modulators have been invented, designed, researched, and developed to date. The research is still going on. This chapter will briefly discuss or describe the classes of modulators in existence and attempt to give insight into the working principle. An optical communication system's essential components are shown in figure 2.1, reference number 19. It consists of a transmitter, a communication channel, and a receiver, the three elements common to all communication systems. Also, the basic component of both the optical transmitter and receiver are shown in figure 2.1. The role of an optical transmitter is to convert the electrical signal into optical form and launch the resulting optical signal into the optical fiber, whereas the receiver converts the optical signal received at the output end of the optical fiber back into the original electrical signal. So now if we look at figure 2.1, so here above the generic communication system structure is shown. That is, we give an input signal to optical transmitter, then the optical transmitter transmit it through communication channel. After that, it goes to the optical receiver, and then we finally get the output. But inside the optical transmitter, what are the components? And inside the optical receiver, what are the components? We can see in the below figure. So here, this communication channel is the optical fiber cable, and the components which are present in optical transmitter are shown below. If we see the components of optical transmitter, there is a driver section, and after that optical sources. So these optical sources are lasers, LEDs, and then this source, this signal which is generated from this laser or LEDs are given to the modulator section. And in the modulator section, with the help of electrical input, the signal is given to the channel coupler, and then the channel coupler gives the information or provides the information to the communication channel. After that, at the receiver end, we can see the channel coupler. Again, one channel coupler is there. So that channel coupler gives the signal to photodetectors. So in photodetectors, what it does is that it converts the signal which is present in light form into electrical form, and then this electrical form is this signal is given to the demodulator, where the demodulation is done by using a decision circuit that identifies bits as ones and of the electrical signal. And also the accuracy of the decision circuit depends on the signal to noise ratio of the electrical signal generated at a photodetector. That's why an electronic part is attached to the photodetector and demodulator in the optical receiver section. After that, at the final output, we'll get the electrical output. So this is what has been shown in figure 2.1. So now coming to section 2.2, electro-optic effects. So there are several electro-optic effects that allow an electrical signal to affect the propagation of light. The most relevant effects in an electro-optical modulator are electro-absorption, carrier density or plasma effect, linear electro-optic or Pocal effect, and quadratic electro-optic or Kerr effect. There are other effects such as an acousto-optic, where the propagation of light is affected by a sound wave that can be used to make modulators, but these are outside the scope of this thesis. So now coming to the electro-absorption effect. In electro-absorption effect, an applied electric field changes the energy difference between the conduction and valence bands in a semiconductor. This changes the absorption of light for photon energies near the bandgap energy. Reference number 20. This occurs in bulk semiconductors, including both silicon and 3,5 group semiconductors. So these 3,5 group semiconductors consist of elements like boron, gallium, aluminum, arsenic, antimony. So these are the materials in this 3,4 semiconductor group. The electroabsorption effect modulates the intensity of light directly, and the relation of absorption to electric field is nonlinear and has no simple general analytic representation. The change in absorption is dependent on the refractive index, reference number 17 and 21. The refractive index change from this source has a quadratic dependence on the applied electric field. This results in optical phase modulation along with optical intensity modulation. The electroabsorption effect is strongly dependent on the wavelength of light, the material used, and temperature, respectively. So the next effect is the carrier density effect. The key characteristics of this effect are that modulation is achieved by varying the density of carriers. This can involve significant speed limitations due to carrier lifetime, which is typically in the 1 to 10 nanosecond range for silicon and 3,5 semiconductors. These speed limitations can be overcome by shortening the lifetime via material damage or by operating in depletion mode where carriers are moved instead of recombined. But these techniques lead to an increase in switching voltage. Reference number 22. Carrier effects are primarily of interest in silicon, where the fast electro-optic effect is absent or very weak. Also, Soref and Bennett, reference number 23, studied results in the scientific literature to evaluate the change in the refractive index to experimentally produce absorption curves for a wide range of electrons and holes densities over a wide range of wavelength. In particular, they focus on the communication wavelength of 1.3 micrometer and 1.55 micrometer. However, their experimental data were updated in 2011, reference number 24, which are as follows. So at wavelength equals to 1.55 micrometer, delta n equals to delta ne plus delta nh, where delta ne and delta nh are the change in refractive index resulting from the change in free carrier electron concentration and change in refractive index resulting from the change in free hole carrier concentrations, equals to minus 5.4 into 10 to the power minus 22 delta capital Ne to the power 1.00 1.011 minus 1.53 into 10 to the power minus 18 delta n subscript h superscript 0.838. Also, delta alpha, which is absorption, equals to delta alpha E plus delta alpha H equals to 8.88 into 10 to the power minus 21 delta capital Ne to the power 1.167 plus 5.84 into 10 to the power minus 20 delta capital N H to the power 1.109. Also, this change in concentration of change in concentration and absorption changes at different wavelengths. So another wavelength is taken, that is wavelength equals to 1.31 micrometer. So at 1.31 micrometer, delta n equals to minus 2.98 into 10 to the power minus 22 delta capital Ne to the power 1.016 minus 1.25 into 10 to the power minus 18 delta capital N h to the power 0.835 and delta alpha equals to 3.48 into 10 to the power minus 21 delta Ne to the power 1.229 plus 1.02 into 10 to the power minus 19 delta nh to the power 1.089, where delta Ne and delta small nh are the change in refractive index resulting from the change in free electron carrier concentration and change in refractive index resulting from the change in free hole carrier concentration respectively. Also, delta alpha E and delta alpha H are the change in absorption resulting from the change in free electron carrier concentration and change in absorption resulting from the change in free hole carrier concentrations respectively. Also, the change in electron and hole concentration is denoted by delta capital Ne and delta capital NH. Now coming to 2.2.3 linear
Give a pause.
electro-optic effect.
Himanshu,
Okay,
give
sir.
a pause here. Yeah, let me explain this portion. Actually, uh, as far as these electro-optic effects are concerned, this there are many phenomena electro absorption where if we vary this band gap according to this change in the band gap, a particular light will be absorbed. So this is the mechanism of electro absorption. Now coming on this carrier density, which is popularly also known as plasma dispersion effect. Plasma dispersion effect, basically, let me see because question is also given here. So plasma dispersion effect occurs basically in, say, PN junction based, optical waveguide. Basically this structure is like this, a rib waveguide structure. Okay, rib waveguide structure in which one side is p type material and another one is the n type material, and we give here some biasings, say some positive and negative. In PN case, basically we apply reverse bias case. That is the depletion mode. We know in PN junction, if we apply reverse bias, then what will happen? The depletion width increases. So this applied potential, which is working as a bias, is now your information signal. So it will be sometimes on, sometimes off, on and off. In this way, what will happen? The depletion width will vary. This width will vary according to the modulating signal. According to modulating signal, this there is a variation in the depletion width. And in this depletion width area, this charge carrier like electrons and holes. So holes are majority carrier in p type and electrons are majority carrier in n type. So there is a change in actual concentration of electrons and hole. So Saurav and have did this have done a experiment and find out this curve with respect to change in concentration of electrons and hole and change in the refractive index. Here let me write E and H. So two curves. So they have observed that there is a with respect to increase in this carrier concentration, there is a change in the refractive index. So two phenomena are coupled here. What is this? Change in electrons and holes, that is electronic phenomena, and change in the refractive index. Change in the refractive index is a optical phenomena. So there we could find a relationship between electrical phenomena and optical phenomena. Optical phenomena is being controlled by electrical phenomena. And what is that? Change in the concentration. Change in the concentration of electrons and hole leads to change in the refractive index. This is what we try to exploit. Although this value is very, very small, but if we increase this length or interaction of light is sent here, interaction of light through the device, then you can get sufficient refractive index change to achieve modulation. But there is a drawback. There is, of course, counterbalancing thing that is called here absorption. That is delta alpha. So this delta alpha is absorption or which leads to loss in the optical signals, which is a kind of undesirable thing. This is where we want to minimize it. Okay, and for two different operating wavelength, that is 1.55 micrometer, which is known as zero loss window, and 1.31 micrometer, that is called zero dispersion window. So for these two empirical results, these are empirical results, no SS for things. These are the curve fitting coefficients, like minus 5.4 and minus 1.53, and this 8.88 and 54, etc. These values are extracted from the curve fitting formula. Similar goes to this one. Yes. With this, any question is there? You can ask any question if you wish. You can write in chat box also. If no, then Himanshu, go ahead.
Okay, so coming to section 2.2.3, linear electro-optic effect. The linear electro-optic effect or Pockel's effect is found in crystals that do not have inversion symmetry. This includes barium titanate, 3,5 semiconductors, lithium niobate, and many other crystals but not silicon. Reference number 25. In the Pockel effect, the electric field applied along a particular crystal axis will affect the refractive index along with one or more of the three principal crystal axes. It is sensitive to the polarization of light and to the direction along which the field is applied. In some case, the electric field can change the direction of crystal axis and lead to polarization rotation. The Pockel effects can be described by delta n equals to minus 1 by 2 n cube r capital E, where small n is the refractive index, delta n is the index change, r refers to the electro-optic coefficient, and capital E is the electric field component along the appropriate crystal direction.
Yeah.
Now coming to
Just wait.
care.
This,
Okay.
this is a Pockle effect, which is used in crystal type of material, and this crystal material is not compatible with the CMOS technology, and that is why the modulator developed on lithium niobate are very very efficient. Although there is 50 Gbps data rate can achieve, but only issue is that it is not it cannot be integrated. Only discrete circuit or devices can be made. So till now, whatever development could take place, it was because of this lithium niobate, which is excellent optical material. Its refractive index is changes with very small voltage also. So this popularly known as this focal effect. So yeah, so most of the time, wherever you have seen, this is the lithium niobate based optical modulator, which works on the focal effect. So this is the electric field. So your see delta n is directly proportional to E. That is the electric field which you applied in the form of modulating signal. And others are the material parameter. Like R is the electro-optic coefficient of that particular material. Okay, yes, go ahead. Kerr effect.
Okay, Kerr effect. The Kerr effect results in an index change that depends on the square of the applied electric field. Like the Pockel's effect, the Kerr effect modulates the phase of light. The effect is generally very small, so when the Pockel effect is present, it usually dominates the Kerr effect. The Kerr effect also accompanies electroabsorption. This effect is present in silicon, although it is very weak. The change can be expressed as reference number 25 delta n equals to S n naught E square by 2, where S is the Kerr coefficient, capital E is the electric field, and naught is the unperturbed refractive index. Now coming to section 2.3, losses in optical waveguides. Losses in optical waveguide can be caused by three main reasons: absorption, scattering, and radiation. All three categories can be further subdivided, although each of these effects contributes to the waveguide design and the material used to fabricate the device. Absorption. The leading cause of absorption loss in optical waveguides can be categorized as band-edge absorption or interband absorption and free carrier absorption. Interband absorption occurs when photons having energy more significant than the band gap are absorbed to excite electrons from the valence band to the conduction band. Therefore, to avoid interband absorption, a wavelength must be used greater than the waveguide's material's absorption H wavelength. The bandage absorption of a material does not make an abrupt transition from strong absorption to transparence, so care should be taken while selecting a wavelength for a given technology. For example, pure silicon has a bandage absorption of 2.83 dB per centimeter at wavelength 1.15 micrometer, whereas moving to a wavelength of lambda equals to 1.52 micrometer, the loss gets reduced to 0.004 dB per centimeter. Reference number 26. Free carrier absorption may be significant in semiconductor waveguides where the carrier concentration affects both the real and imaginary refractive indices. The Drude-Lorentz equation can describe the change in absorption in semiconductor. Reference 23 and 27, where the change in absorption, that is delta alpha, equals to E cube lambda naught square by 4 pi square C cube epsilon naught n into capital NE divided by mu E into m subscript CE superscript star whole square plus capital NH by mu H into m subscript CH superscript star whole square, where E is the electron charge, C is the velocity of light in vacuum, mu E is the electron mobility, mu H is the hole mobility, M subscript C superscript star is the effective mass of electron, M subscript CH superscript star is the effective mass of holes, capital NE is the free electron concentration, capital NH is free hole concentration, epsilon naught is the permittivity of free space, and lambda naught is the free space wavelength. Some of the parameters in the equation are independent, so care must be taken when evaluating the free carrier absorption. Now coming to section 2.3.2, scattering. Scattering is a random change in the direction of particles constituting a beam or wavefront due to collision with particles of the medium traversed. Scattering in optical waveguide can be categorized as volume scattering and interface scattering. Volume scattering is caused by imperfections in the waveguide material such as void, contaminants, atom, or crystalline defects. Interface scattering is due to the roughness at the interface between the core and the waveguide's cladding. Volume scattering is minimal because of improvement in sufficient levels before fabrication of the waveguide. However, it should be considered for new experimental materials. And interface scattering may not be negligible, even for a well-established material system, because the loss can be significant even for relatively smooth interfaces. Coming to section 2.3.3 radiation. Radiation loss is ideally negligible for a straight optical waveguide. Such kind of loss implies leakage from the waveguide into the surrounding media, typically the lower and upper cladding. Reference 1. For a well-designed waveguide, radiation loss is not significant. Although unwanted perturbations in the waveguide due to slightly damaged fabrication mask may cause scattering of light from one mode to another. Also, the waveguide's curvature may induce some radiative loss in the waveguide, as this will result in a change of the angle of incidence at the waveguide wall, which may result in some relative loss.
Yeah, give a pause here. So we come to know, as far as losses are concerned, there are three phenomena which can occur in the optical modulator. First, it is absorption. Because of the absorption of the light in a waveguide, which is doing a task of modulation. So, see, if the principle, if we are not using the electro absorption principle for optical modulation, then this absorption loss is a drawback. Himanshu, you mute your microphone. Himanshu, mute your microphone. Okay, thank you. So, if your optical modulator is not working on the principle of electro absorption, then this absorption works as an undesirable phenomena, and it will lead a loss of the optical signal. However, whenever we are using this optical modulator based on the electro absorption, then this loss because of the absorption is advantageous. Why? Because we want, whenever signal is not there or we are sending a logic low signal, then light should not appear at the output. How it will occur? It will occur when the device will completely absorb the light inside it, so that we will not get the output light at the output terminal. So this absorption phenomena can be used judicially or more wisely in electro absorption modulator. However, if we have say plasma dispersion effect based modulator or other modulator, then this absorption is a loss mechanism and we have to minimize it. Another another reason which we have seen this loss is scattering. How scattering occurs? Actually, when a particular light is coming having say lambda is the wavelength, suppose 1.55 micrometer, that is the some length or some dimension 1.55 micrometer, and the light which is passing through that medium has also some smallest particle in that medium, and if the particle size is corresponding to the wavelength of that light, what will happen? They will scatter. See, there will be no scattering if either particle size is very large or very small. If very large, will pass. If very small, also will light will allow. So there will be no scattering. However, as soon as the size of the particle in that material is almost equal to the wavelength, then it will interfere in the path of the light and it will divert the path. That is called scattering. Okay, so this is one of the reason of loss in the optical waveguide, which is used as an optical modulator. And third one is the radiation loss. Radiation loss occurs if waveguide is there. If as soon as if it is straight waveguide, then radiation loss is negligible. Why? Because we already have optimize the waveguide dimension in such a way that light should be supported. Light should follow the say total internal reflection or light guiding principle. Whatever its condition is there to support that light. Okay. However, if waveguide is bending. If waveguide is bending, at the bending, what happens? There is a deformation in the dimension of waveguide. That will why what is called uh, break that condition of light propagation, say total internal reflection. Then because of that, there will be radiation of the light because of, say, evanescent field, etc. So that radiation of light will will lead into the loss of light. So that these are the three phenomena. One is the absorption, another one is a scattering, and third one is the radiation. However, from understanding point of view, these three things are given here. For our, since our modulator is based on the electron absorption phenomena, so that absorption, which is a kind of loss, we are using it for useful purpose. Any question, participants, till now or before also? If not, then we can go to next section, that is 2.4. Over to you, Himanshu.
Okay, the section 2.4 is performance matrices of optical modulators. So, first of all, we'll go through insertion loss. Insertion loss, denoted by IL, is a significant parameter of optical switches and modulators. IL is essential to design a device or a system. It is generally expressed in decibels, dB. For the case in which the modulating signal acts to decrease the intensity, it is given by reference number 11723, IL equals to 10 log I subscript T by I naught, where IT is the optical intensity that would be transmitted by the waveguide if the modulator were absent, and I naught is the intensity transmitted with the modulator in place but with no applied signal. Coming to 2.4.2 extinction ratio, one crucial characteristic of optical modulators and switches is the extinction ratio ER. The ER is similar to modulation depth or modulation index eta. In the case of an intensity modulator, the applied electric signal acts to decrease the intensity of the transmitted light. Eta is given by eta equals to I naught minus I by I naught, where I denotes the transmitted intensity and I naught is the value of I when no electric signal is applied. Now, if the applied electrical signal is used to increase the transmitted light intensity, then eta is given by eta equals to I minus I naught by Im, where Im is the transmitted intensity when a maximum signal is applied. The maximum modulation depth or extinction ratio is given by Nmax equals to I naught minus Im by I naught for Im less than equals to I naught, or eta max equals to Im minus I naught by Im for I naught less than equal to Im. However, the extinction ratio and figure of merit FOM for an electro-absorption modulator can be defined by 127 AR equals to IL offstate minus IL onstate, where FOM is figure of merit equals to IL offstate minus IL onstate divided by IL onstate, which can be signified by alpha offstate minus alpha onstate divided by alpha onstate equals to ER by alpha onstate. So IL offstate or alpha off denotes the offstate of the device when a minimal amount of light is allowed to pass through the waveguide due to maximum absorption. Similarly, IL onstate or alpha on denotes the onstate when the maximum amount of light is allowed to pass through the waveguide. Now coming to section 2.4.3, energy consumption. Electro-absorptive devices necessarily absorb some fraction of the input power, since that is how they modulate the signal. The absorption leads to additional mechanism for energy consumption. Reference 28. When sending actual digital data, it is reasonable to expect equal number of ones and zeros. Therefore, on average, there is one complete charge discharge cycle every 4 bits in an effectively random sequence of bits. So the total dissipated energy consumption per bit is given by delta E subscript bit equals to 1 by 4 CV square, where the capacitance and applied potential is denoted by C and V. Now coming to 2.5 types of optical modulators. Various types of modulator have been designed to date to improve the performance capability of the device. Depending on the material used to design the device, the modulators can be classified as follows. Silicon high-speed modulator. Silicon is one of the most studied semiconductor in history and literature is widely available. It has a crystalline structural. Silicon exhibits optical properties defined by crystal symmetry and the indirect bandgap. These properties define the approach used to manipulate light in silicon via an applied potential. Silicon is a centrosymmetric indirect bandgap semiconductor with a bandgap energy of 1.12 electron volt, which corresponds to optical absorption below a wavelength of 1.1 micrometer. McFarlane et al. Reference number 29 measured the absorption edge with increasing temperature, and the results showed that even at relatively higher temperature, 415 Kelvin, which is equals to 141.85 degrees Celsius, the absorption band shifts towards lower photon energy and approaches minimal absorption loss below approximately 0.95 electron volt, which corresponds to a wavelength of 1.3 micrometer. Therefore, even in higher temperature environment, often found in high-speed electronic integrated circuits, silicon is suitable for transmitting telecommunication wavelengths between 1.3 micrometer and 1.55 micrometer. The device's electric field is also influenced by the doping concentration of the n-type and p-type region. The free carrier concentration affects both the real and imaginary part of the refractive index, and this can be explained theoretically by the well-known Lorentz equation shown in equation 2.11. Figure 2.2 shows a silicon optical modulator based on a metal oxide semiconductor capacitor. Reference number 30. The schematics diagram of the silicon-based optical modulator demonstrated experimentally to exceed 1 GHz bandwidth fabricated using complementary metal oxide semiconductor (CMOS). The structure comprises an N-type doped crystalline silicon slab, the silicon layer of silicon on insulator wafer, and a P-type doped polysilicon rib with a gate oxide sandwich between them. The free carrier plasma dispersion effect is used to achieve modulation of the refractive index in silicon. A MOS-type capacitor phase shifter is used to realize the charge density modulation. Under accumulation condition, the majority of the carriers in the silicon waveguide modifies the refractive index to induce a phase shift in the optical mode. The advantage of using a MOS capacitor phase shifter is the high achievable modulation speed, and there are no slow carrier generation or recombination process involved in the accumulation operation. However, silicon modulator speed is limited as it is dependent on the device configuration and how fast the free carrier are injected removed from the optical waveguide.
I'll give a pause, Himanshu.
Okay, sir.
So, as far as the silicon high-speed optical modulators are concerned, we have three principles. One is called this uh, carrier depletion-based optical modulator, in which we use PN junction in reverse bias condition. Carrier uh, carrier accumulation, that is this MOS-based capacitor, and carrier injection-based modulator, that is PIN junction based optical modulator. So in PIN junction, we make it forward bias. We inject the carrier. That is why injection based. In PN junction based, it is depletion carrier based. Means we make PN junction in reverse bias condition. And third one is this MOS capacitor. So one of our MTech scholar did the work on this MOS capacitor based optical modulator. Some characteristics is change in the carrier concentration, change in the refractive index, and hence modulation can occur. So in past, one or two students did the task on this. However, in thesis only it is mentioned from knowledge point of view. Okay. So any question? No, then we can move. I think if question comes, then it will be good. Don't be a passive listener. Atikur, Bhargavi, Ayushi, and others, including Malvinder, for clarification or something like that. If not, then we can move to next section, that is 2.5.2. Over to you.
Okay, coming to 2.5.2, it is electro-optic polymer modulator. Polymer-based optical modulators have been investigated and developed by researchers to date, reference 31 to 33. Compared to crystalline materials, their advantages are the ability of chemists to molecularly engineer organic materials to achieve a very high electro-optic coefficient, and the ability of the device engineer to use spin cast fabrication technology and to therefore potentially integrate electro-optic devices with other optoelectronic devices and circuits. But the reputation of polymer-based modulators is mostly questioned because of their instability. Reference number 25. The instability concerns are long-term temperature stability of molecular alignment and the electro-optic coefficient, the optical losses of the waveguides fabricated from the materials, the photostability after long-term exposure to laser radiation. Figure 2.3 shows the cross-sectional view of a polymer-based modulator. The structural design is based on calculating the refractive index of the waveguide. The design procedure and material characteristics are discussed in the literature of M. Ho et al. Reference number 34. So figure 2.3 shows the cross-sectional view of a buried ridge waveguide showing the Maxender two arms. So here UFC 170 in figure number 2.3, UFC 170 and UV15 are curable epoxy layer, or you can say they are the claddings. They are the class of cladding which are manufactured by Masterbond Corporation. And this CLD slash APC is the polymer, that is amorphous polycarbonated. So here the polymer is sandwiched between two cladding layers, that is UFC 170 and UV 15, and then the light is allowed to pass through one side to the other, and they are calculating the refractive index. So in details, if we want to go through, then we have to go through reference 34. Here just the diagram or a figure is shown. So coming to 2.5.3, complex oxide electro-optic polymer. So one of the significant achievement in optical ceramic was the development of transparent ferroelectric oxide, that is PB subscript 1 minus x LA subscript x ZR subscript 1 minus y TI subscript y 1 minus x less 4 O3. So in short term, this is named as PLZT. So the molecules or the substance used here are lead, lanthanum, zirconium, titanium, and oxide. So in short form, it is known as PLZT. So here PLZT with a composite of PB 0.92, LA 0.08, ZR 0.65, TI 0.35, 0.98, and O3 was first produced by Hartling and Land at the Sandia National Laboratories in 1969. Reference number 35. The incorporation of lanthanum La ions into the lattice enhances the densification rate of lead zinconide titanate PZT ceramics, leading to homogeneous ceramic microstructure. The advantages of PZLT includes high optical transparency from visible to mid-infrared wavelengths, large EO coefficient, fast EO response, solid state nature, and the ability to make it into large crystals. The potential as thin films and its ability to integrate with other optical materials and semiconductors. The PLZT can be used in applications, reference 36, such as displays, ultrafast optical shutter, optical tunable filters, EO modulators, reference 37, and polarization compensator. Figure 2.4 shows the design schematic of the PLZT waveguide, reference 3738. The PLZT waveguide is deposited on top of the thin photolithographically patterned ITO spacer. The propagation loss at 1.55 micrometer was 2.7 dB per centimeter. The extinction ratio for the short 3.5 mm MZ waveguide EO modulator was observed to be 14.4. So figure 2.4 shows the schematics of a PLZT waveguide. So now coming to 2.5.4 gallium arsenide modulator. High-speed optical modulators are primary components in photonic integrated circuits (PICs). Therefore, the materials must have suitable electro-optical properties, limiting the practical choice to 3-5 semiconductors, ferroelectric ceramics like lithium niobate, and electro-optic polymers. Reference 25, 39, 40. Gallium arsenide (GaAs) is a good choice for millimeter wave devices because of its high electron mobility, availability of low loss semi-insulating substrate, environmentally stable, and lacking undesired pyroelectric effects. These properties make gallium arsenide suitable for high-speed modulator technology. The devices utilizing gallium arsenic are linear and well suited for zero chirp applications. It is a low cost technology for both raw material cost and process route compared to indium phosphate. The design of a conventional gallium arsenide based EO modulator is shown in figure 2.5. Reference number 41. In this structure, the optical mode confinement in the vertical is based on the refractive index difference between gallium arsenide core and GaAs equals to 3.4 and the aluminum gallium arsenide cladding and AlGaAs equals to 3.
Yeah, give a pause here. So here we come to know different types of optical modulators. Just only working principle, advantages and disadvantages have been shown. What is the purpose of giving here? Though in this thesis only one type of modulator has been taken up and its design has been optimized and result have been published. However, mentioning other type of optical modulator is not only for the purpose of for the purpose of explaining other modulator, but it opening the window for other researcher that yes, there are other types of modulator where research can be done, which are contemporary in nature and people are working on that. So over to you, Himanshu. One call is coming.
Yes, sir. So coming to section 2.6, the mathematical modeling of directional coupler based optical modulator. A directional coupler, as the name suggests, couples the energy traveling in a waveguide to the other when kept in close proximity to one another in a particular direction. Directional couplers are used for splitting and combining light in photonic systems. The coupling between the waveguides when they are in close proximity to each other can be addressed by the couple mode theory, as shown in figure 2.6. The electric field in the propagating modes can be described by reference 42. So here in figure 2.6, it shows the diagram of a directional coupler. So here there are two waveguides, waveguide 0 and waveguide 1 with refractive index N2. Both the refractive index are same. Here we are assuming that both the waveguides are identical. Now here Az is the complex amplitude which includes a phase term exponent minus j beta z, where beta is the propagation constant in z direction. The term is the solution to the field distribution of the modes. Therefore, the power in waveguides, say waveguide 1 is given by P1z equals to A1z square. Now, the coupling between modes is given by the general couple mode equations for the amplitude of the two modes. That is d a naught by dz equals to minus I beta naught a naught z plus k01 a1z. This is for waveguide 0. Now for waveguide 1, it is d a1 by dz equals to minus I beta 1 a1 z plus k10 a naught, where beta naught and beta 1 are a propagation constant of the modes in the two waveguide, and k01 and k10 are the coupling coefficients between the modes. Considering the waveguides to be identical and they both have exponential optical loss of alpha, then beta is given by beta equals to beta r minus I alpha by 2, where beta equals to beta naught equals to beta 1 and beta r is the real part of beta. Also, k 01 minus k10 equal to, sorry, k01 equals to k10 equals to minus ik, where k is real. Now using the above equation, if we substitute in the previous equation, that is for the, that is the equation in general, that is a general couple mode equation, we will get this following equation, that is d a naught z by dz equals to minus I beta a naught z minus k a1 z, and d a1 by dz equals to minus I beta a1 minus k a naught. So here beta, since the two waveguides are identical, that's why we have taken beta naught beta 1 equals to beta, and the coupling coefficient, that is k01 k10 equals to k, since we are assuming that the two waveguides are identical. Now, if we assume that the light is coupled into the waveguide 0 at point z equals to 0, so that the boundary condition of the problems are given by a naught 0 equals to 1 and a1 0 equals to 0, then the solution are described by a naught z equals to cos kz e to the power minus beta z, and a1z equals to minus sine kz e to the power minus j beta z. Thus, the power flow in the waveguides is given by P naught z equals to cos square kz e to the power alpha z, and P1z equals to sine square kz e to the power minus alpha z. Also, the coupling coefficient is given by k equals to 2h square q e to the power qs divided by beta w into q square plus h square, where w is a channel width, s is the separation, h and beta are the propagation constant in the y and z directions respectively, and q is the extinction coefficient in the y direction. Now coming to section 2.7, applications of optical modulators, the progress and success.
Can we give a pause little bit here?
Okay, sir.
So here two waveguides are there. They are in the very nearby. They are vicinity to each other. So when light is traveling through one waveguide, it will interact with the other waveguide. And we know through the coupling coefficient what happened after traveling certain distance, entire light is transferred to the another waveguide, and then traveling in another waveguide after certain distance, the same light will come back to the first waveguide, and so on. So this is called coupling mechanism. So through equation we come to know that there is a light is propagating in one, then it transfer to another, and then so on. So its behavior has been described with the help of Maxwell equation. Then solving this Maxwell equation after applying boundary condition, and then we get the solution of it. And the solution is written here. And this solution, if you code, if you write a code of this solution, so you will get nice plot of electric field intensity. Okay, with respect to distance. So that kind of phenomena is described with the help of coupled equation. Okay, so with this, now we can move to next section. If no question is there, however, we will appreciate if any question is coming. Over to you, Himanshu.
Okay, now coming to section 2.7, applications of optical modulators. The progress and success of semiconductor lasers and detectors, the steady advances in waveguide optical devices, and the realization of single mode optical fiber and connector technology have sparked an explosion in the field of research and development on integrated optical devices. The primary application of optical modulators is in the field of digital fiber optic communication. Various types of optical modulators function differently depending on the type of design and the material used to develop the device's structure. Optical modulators are used in electric field sensor, millimeter wave imaging, optoelectronic oscillators, electro-optic analog to digital converters, fiber optic gyroscopes, and polarization insensitive devices. Also, many applications requires modulation at a single or mixed frequency. Such kind of modulators are used in interferometric applications as well as in low frequency locked-in detection schemes, laser stabilization, phase sensitive detection, and pump probe detection scheme. Coming to section 2.8 summary, a summary of this chapter is as follows. Section 2.1 gives a brief discussion of the basic component of optical communication system. Section 2.2 discusses various electro-optic effects that affect the propagation of light in the waveguide. The effects such as Pockels effect, Kerr effect, electroabsorption, and carrier density effect have been discussed briefly. Section 2.3 discusses the cause of losses in optical waveguide, the reason behind the losses such as absorption, radiation, and scattering have been discussed in brief. The performance matrices of an optical modulator in terms of IL, ER, FOM, and EBIT have been discussed in section 2.4. Different modulator types depending on the material used to design the device have been discussed in section 2.5. The coupling phenomena in a directional coupler based optical modulator is discussed in section 2.6. Section 2.7 discusses the applications of optical modulators and their uses in the present scenario of communication.
So, thank you, Himanshu, for completion of this chapter 2. Here, although here we are discussing about optical modulator, I would like to draw the attention of all participants that there is a big program called LIGO. LIGO means laser interferometer gravitational gravitational wave observatory. You have heard that few years back, the scientists who have discovered or could identify the gravitational waves. In universe there are gravitational waves. These gravitational waves occasionally strike with the earth and it deforms the shape of the earth. These gravitational waves are very very weak and it is very difficult to detect its occurrence. So CERN, that is the big laboratory, and they have made they have made a very large interferometer, that is a kind of magenta interferometer base. Uh, More specifically, let us call it interferometer only. Interferometer, the way we study magenta interferometer, same kind of structure. So that interferometer detects the presence of gravitational wave, and it is so important that even government of India has also taken up this issue and they have established a laboratory in Maharashtra, LIGO laboratory, LIGO India. So there, in the recent past, I was trying to learn how India is progressing in this LIGO project. So people from different part of the country, they sat together. It took almost 9 to 10 years to write down the project proposals, its feasibility, how to implement, and now it has come into the picture. Is that laboratory? So underground, path is created so that there should be no interference from outside. And then whenever light is going this side, after reflection, they will come back again. And if gravitational wave is touching to the earth, so there will be some bulge, something like that, some disturbance will be there. That kind of disturbance will be detected with the help of LIGO observatory. So this is all, this is all good application of optical phenomena. So there are ample opportunities. Those people who have written that project, I know they are very very old now. They are going to retire. I think many of must have retired also, because it is already took 10 years to write and establish that laboratory, and after that to execute, to work further in this legal laboratory. We need expert people, we need manpower, we need trained manpower who have well understanding, well, who has good understanding of this optical phenomena, particularly this interferometer. So this is where I want to draw your attention that if you pursue research work in this field, there are ample opportunity to work into, to work into. If you have enough competency, skill, ability, you will easily absorb and you can make your career bright, as well as you can help to nation, society, and your family. So with this, we can, from my side, it's over. Now, if anyone wants to ask the question, that shall be great. You can write in chat box also. Anyone or any comments? Indrani, any comment
No,
in
sir.
that?
Nothing as of yet. I'm following it, but it's still a little, a little lost sometimes.
Okay. So chapter 2 is completed. Now, tomorrow we will sit together to read this chapter 3. Thank you for being here, for giving your valuable time. Even say 30 to 40, 50% if you are able to absorb it or able to get it, that is a success. That is a sign of our success. No problem. Being a undergraduate student, we do not expect too much. But thank that your aptitude of learning is very much appreciating.
Thank you, sir.
Thank you, sir.
Thank you, Ram, Atikur. So I will stop this recording.